Welcome to everyone for this last morning session. And we begin with Jasmin Raissy, the action activities of okay. And we're going to talk about the sales. Now, this is going to talk to us about a unified approach to a geometric approach to parabolic jumps.
Thank you very much. So, well, let me start by thanking Filippo, Hervé, and Andy for this kind invitation. It's always nice to get back to Italy, my birthplace. And I don't know, I mean, I'm not the last one to say that it's wonderful to give a lecture in such a beautiful room. I mean, on Monday when I teach in Bordeaux, it's going to be so sad. I will not have any fresco with me. So today, what I'm going to talk about is, well, the idea is to, if I get to tell you something about joint work, which is unfortunately still in progress, but now that I'm no more to lose, maybe we will finish that with my former colleague, joint So, but as I was saying, well, if I manage to get there, because my idea for today's talk is to give you some hint of what you can do and why you want to study parabolic curves. So if you don't know what a parabolic curve is, at least at the end of this morning, I hope that you will know what it is and why you're interested in it. So we want to study, we're doing holomorphic dynamics, so I'm not doing any Kobayashi hyperbolic stuff, but if I manage to get there, we will see some hyperbolicity and some distances later on. But we're doing dynamics, so we are taking a holomorphic map. Itself acts as a complex manifold. I'm now interested in its dynamics. So I want to know what happens to dehydroids in a long time. So I want to know where they accumulate. I want to know something about that. And of course, when you do something like that, you have two ways of seeing it. You can look at dehydroids for the global map. So I have a holomorphic map on X itself. And I want to know what happens on all of X, okay? And I can study where the family of dehydroids is normal, which is the place where I should be able to understand what happens to the dehydroids, what happens to the limit, and the limit will depend continuously on the initial point of the orbit. Or, of course, you could have you could study the complementary set, which is called usually the Julia set. I will not speak about Fatou and Julia today, but you know, well, I have to. I'm French, so you have to speak about French people also. No, sorry, I'm just kidding. I cannot see you smiling because you all have masks, so it's a bit complicated. Anyway, so you can smile out. So you have this Fatou set, which is where you should be able to understand what happens to the dehydroids, and the Julia set, where you will have chaos. So usually what we say is like, this is studying the dynamics globally, from the global point of view. But you could also tell yourself, okay, look, there are a bunch of points on this system which should be easier to understand. Like, for example, fixed points or periodic points. Well, actually, periodic points are just fixed points for one of the dehydroids. So let's consider fixed points. Fixed points don't move. And I could ask myself, okay, I have a fixed point, what happens in the neighborhood of the fixed point? So I'm going to do local dynamics. After considering an dehydroid, I will consider a fixed point. Structure that the holomorphic structure that I have on X, I will simply go back to Cn. And actually, even more, I have a fixed point I can choose coordinates and I can put it at the origin. So now I have the jet. Let me call capital it's always the name of this plane. But CP0 itself, and I have jet. And then we have here. Now, what I want to know, what the question is what happens to you guys? Yeah, the origin. So the origin is fixed. At 0 and 0. I get a small neighborhood, as small as you want. Fix one neighborhood. The map is standing this neighborhood itself. It is small. I get it here. I iterate, and I want to know what happens to the secrets. Are they going? Well, the first basic question is: are they going to stay always in this neighborhood that is fixed, or are they going to all go out in front of many stuff? If they do, then since I'm just considering a term, I cannot say anything now. I mean anything more, because they could maybe go back, like exit from this neighborhood and then go back from this spot. I will not see it, okay? Because I'm studying it locally. And you could ask another question. Okay, say you know how to describe the local dynamics, your fixed point. Who cares with respect to the global dynamics? This is natural. This is a natural question. Do these global and local dynamics will somehow interact? What happens if I know the global dynamics and I know the global dynamics, the local dynamics, and the other way around? So it turns out that when you know information on the local dynamics in a fixed point, that is not missing, you can infer information on the global dynamics of the map. On these were two cells that I was talking about. And I didn't put on the paper because I don't want to talk about it today. Okay, so the dream goal is to understand everything in the neighborhood. Sorry. Good. Yes. And when you do something like that, what happens is that, well, the first thing that you want to use is the fact that you have some coordinates. You are the neighborhood of a fixed point, or map, so you can write it locally. Okay, so locally your map, this is very important. And writes like it's a map part plus iota. And so in principle, you would say, okay, first of all, let's forget about the higher order terms and let's study just the dynamics of a linear part of a linear map. That's already something. And then you could ask yourself, okay, I chose some coordinates where I was able to write down my map as a local homomorphic somewhat better series. Can I choose better coordinates so that I can get rid of these higher order terms? Okay, so if I know what happens with a linear map and I can kill all the other terms, then I'm fine. Right? Cool. The point is that so you could work, so this could lead to a linearization problem. And well, it depends whether you are in dimension 1 or higher dimension, what happens in this kind of cases. But I'm pretty sure that you'll see a problem in doing this kind of stuff when the linear map is the easiest linear map that you can think of, the trivial one. If lambda is the identity, and my map is not the identity, it's not a trivial map, then when I iterate, it is not the trivial map. I mean, it's just say I have an isolated fixed point. If I have an isolated fixed point, then my map is not the identity because she fixes, well, this big map fixes everything. And Well, I cannot do what I was trying to do here. Study the linear part, but the linear part doesn't know anything, and then try to kill all these other terms. I will not be able to kill all these other terms. So when you study the dynamics of a map, which is tangent to the identity, then this approach doesn't work. This cannot tell you anything about your dream goal. Okay, so this is not a good approach. The linear term of x, its differential derivation is the So now today, what I'm going to work on is exactly this case, this second case. So I'm going to study maps tangent to the identity, which are not the identity. Because otherwise, well, the identity of everything is fixed, nobody cares, everything is fine, but it's the identity to be fine. Okay, so now my subject. I have a map, origin, and tangent to the identity. And so locally, horizontally, writes like, well, z, the identity, plus, and I'm going to write down the first linear term. And so what I'm using here is with the standard, I'm using the decomposition of x and its homogeneous polynomial parts. Okay, so HK is a homogeneous polynomial now of K plus 1. Okay, so as any story, yes, fine. I'm not consistent in my notation with this. So, and K, of course, is at least 1. And what I'm asking is that HK plus 1 is not 0. Okay, so it's not trivial. Fine. As any story, well, reasonable enough, what now we want to do is, okay, we want to understand what happens with CP. Let's start from the easy case. Well, this should be easy. The case of dimension 1. Okay, so if P is 1, then all I'm saying is completely classical and goes back to other two French guys, called still Fatou, and another French guy, his name is Lo. Okay, so we have, well, the dream goal is good, it's fine. So, anyway, so we have the Fatou, here. Well, let me say it like this, tells us, well, yes, a complete description of the dynamics in the neighborhood of the. So I'm not going to write down the statement of the Louvre-Fatou theorem, which is quite painful to write it down. But what I want to say to you is, well, let's try to see the idea behind it in dimension 1 for a baby case. So, primarily, the baby's case that I can think of is, so let me write an example. I take C, D minus D. Okay, this is my favorite example for explaining the Gromov theorem because it's easy to understand. So what's happening here? Well, let me write it like this. I'm in the context. Where the positive side stated here, they are taken pointing here, is minus 1 minus C is more than 1. It is real and it's smaller than 1. Okay? So whenever I iterate, well, this is something like a linear map. It's not the same. It's not an autonomous iteration. Still, I'm getting smaller and smaller. And so whenever I do this positive real axis, all iterates in a small neighbor of the origin are going to converge to the origin. Okay, what happens whenever so I'm going to use a choke which is not seeable still, just the other colors. So this is the orange one. Whenever we're at this side of the plane, and this negative real line, well, if z is real and negative, 1 minus z is bigger than 1, okay. No more. So what's going to happen is I'm going to be repelled. In principle, you could go back from the other side. No? Okay, you don't know it. I mean, I'm just saying that in front of my step, I exit. I went out on this small visual. See it so far? Well, now you should raise from your chairs and say, look, you were going to tell us that you could have a complete description of in a neighborhood. This is a line, a real line in C. But what happens is that, well, now let's take a small sector around this positive real axis, and let's take a small sector around the other one. Well, this is a little painful to do if you do it near the origin, but if you change coordinate to W is around Z, then what happens is that the origin goes to infinity, and in the image, I'm achieving a little bit. You could find a right half plane, but what happens to your map is that your map stands W, and W plus 1 plus, well, something. Maybe I don't want to do the computation. I should have changed it to choose another. Okay, who cares? What happens is that this is going to be small whenever W is big. It's just acting like the translation by 1. Okay, and so you see that you can find a non-prime region where you're going to go to infinity, and also you can say more, you're going to go to infinity tangentially to this positive real axis. Okay, and so you go back. What happens is that in this kind of sector region, you're going to converge to the origin tangentially to your positive real axis. And on the other side, you're going to, okay, you would like to say you're going to go out tangentially to something. No, let's be precise. You consider the inverse of that. For the inverse of that, this will be somehow an attractive direction. And this sector will be central to itself and orbits will go towards the origin tangentially to the negative axis for the inverse. Okay, I know I'm annoying all the experts, but some of you are not experts in this, so let me be a little easy for today. Okay, it's Friday morning. Good. Still, you should tell me. Okay, look, we're good. Now you have an open neighbor, but still, it's not a full neighbor of the origin. Now you have to trust me. Okay, well, somehow actually not me. You want to too. You can see their proof. And what happens? Okay, let me erase this because otherwise you can't see. What's going to happen is that you can find some sort of pedals, and this is why the name is the Gromov theorem, intersecting. And this attracting pedal, you're going to converge to the origin tangentially to the real positive axis. In this repelling open pedal, you're going to converge to the origin tangentially to the negative real axis for the inverse. You're going to go out. And then you ask, okay, what happens in the middle? Well, in the middle, you first go out from the repelling pedal, and then you go back to the attracting pedal. Okay? And now, well, these pedals are open sets. The origin is the boundary, so you take the reunion of these two pedals plus the origin. Yeah, a full neighborhood of the origin where you know exactly what happens to the locals locally. Okay? If you're here, you go out to find any kind of stuff. If you're here, you go to the origin to course in this direction. And if you're in the origin, you stay in the origin. Okay. So now we're looking at this baby example. I hope you trust me if I tell you that, well, in here I didn't add any other iota terms, but if I add them, they will only enter and start. If I had iota terms, they would be in here. We would change this, but they will not change the picture. So, well, if you add a Q, say now, you can have terms. Terms doesn't change the picture. And moreover, if now, so in the general situation, if now you have f of z, which is z plus a plus 1, z plus 1 plus etc. Well, first of all, you can change linearly coordinates so that here you can have minus 1 over k. And the one is well, the minus comes from here because I want to get back to this kind of picture, and the 1 over k is to make it nice so that I still have a change of coordinates sending the map to the translation by 1. Okay. Otherwise, you are translating by a constant, and well, you know, constants can be anything. Fine. Okay, and if you do this, what's going to happen? You will have, sorry, it's really annoying this. Okay. You will have K repelling direction, which gives you K attracting petals. K repelling directions, giving you K repelling petals. And each attracting petal intersects 2 repelling petals. Okay, well, let me just write down who the attracting direction are. Well, these are vectors, so a vector. So that's what? You listening? You still awake? What do you have in here? Fine. V to the power, so you have direction, so that V to the power k is what? Is real and positive. Okay. And you find direction of the other. So let me put a nicer picture. Yes. Maybe I'm destroying the blackboard, or maybe not. Who knows? We'll see later. I'm lazy. So what happens if k is say equal 3? Well, you're going to have something like this. These are having directions. And now you see the problem. Okay. Well, actually, you can be more precise. I mean, when I say the local product theorem tells you everything, it's because you can also say, well, you know, you remember I was saying, oh, I can choose a coordinate so that I'm going towards the translation by 1. Okay, I change time. So I conjugated my dynamics to the translation by 1. Actually, on each attractive petal, what you have is that you have a quadruplet. That C, so I conjugated it to the translation by 1. So write it down correctly. I always get it wrong. Yes, I'm not following alone my notes. That's fine. And this is the type. Okay. It's type plus 1. And more, more important, whenever you are inside here, and you consider the anti-rate of the initial points, and you have V0 from here, well, this will converge. Not only it will converge to the origin tangentially to this real positive axis, but, well, actually to this attracting direction in this case, but you can also say, it's going to go there like 1/n. So, yes. In this case, yes, I'm pretty sure it's this. It's 1/n to the power 1/k. Usually I do this part in the k equal 1 case, so I don't get mistaken. Okay, and you can also say something from the, oh yes, no, let me be even more precise. The attracting direction. All right, so what did I want to tell you more? Yes, you can be also less precise from the homomorphic point of view. You can consider the topological simplification, so what happens from the topological point of view. And well, this is well, kind of more complicated and more recent, but you also have a complete classification from the topological point of view. So let me just spend 1 minute telling to you why this kind of result, which is quite old, I didn't say it, but lo and behold, that, like, since a while now, and this theorem that usually we find in books, like beginning of, well, 1900s, something like that. So it's 1904. This is what I remember. So how can you use this kind of result, which is quite local, to infer something on the global dynamics? Well, okay, a parabolic fixed point, a fixed point of this kind cannot stay in the F2 set. Okay, fine. But this is, well, here, okay. This is still classical. But you could try to use, well, actually, this is what is done. This F2 coordinates and this attracting and repelling behavior, you can try to perturb it. You can try to start from the baby example. No, I'm not doing it again. The baby example, yeah, sorry. Once was good, maybe twice now. So you can try to perturb your map and say, okay, look, what happens if I add a small perturbation? So my fixed point is going to split into 2 fixed points. Can I say something on the iteration of this perturbed map? Can I do some, can I say something about the dependence on the parameter? And this leads you to what is called parabolic implosion. And parabolic implosion techniques, well, they rely on the existence of the 2 coordinates. And by using parabolic implosion techniques and other stuff, which is more technical than what I'm going to tell you today, for example, Xavier Buche and Arnaud Chantal were able to prove this, their result on the positive Lebesgue measure of the new Julia set, and etc. So there are plenty of reasons why you could try to study this kind of dynamics, but the very first reason is you want to understand what happens. Good. So now you ask, now let's go back to the dimension of these 2, and the question is, what survived? And higher dimension. Can I find a low photon flower theorem? Wow. From my point of view, it would be nice, wonderful, if you could have a 2-dimensional, say you're in dimension 2, a really a 2-dimensional thing with all these petals intersecting, because this gives you a description in a full neighborhood of the origin. Right. But you could ask for something less. You could ask, okay, can I at least find a 1-dimensional one? Okay, and so you could search for, so should we search for 1-dimensional? three-dimensional ones, and so on and so forth, going to dimension B, so open panels. Open domains. And so whenever you are in this situation, you call a one-dimensional pedal. I know Marco is going to kill me because I'm being very skippy. I'm being very skippy with the definition of a parabolic curve, but well, I think you can now read it in any of the papers dealing with this. The idea is that I'm trying to look for a one-dimensional pedal in a, well, higher dimensional world. Okay, and what I want is having something exactly like this, but this is just a one-dimensional pedal. So this is a parabolic curve. Well, everything that stays in the middle is usually called a parabolic submanifold or manifold, depending on orders of dimension or dimension. It depends on how you want to say it. So say parabolic manifold. And in here, well, the maximum dimension ones, so open set, like they should be, these are parabolic domains. And of course, well, you try to do what you can. Okay. And trying to do what you can is also trying to get, I'm really not doing my notes, I'm sorry about that. Trying to do what you can is also trying to find what could be a good analog of this attractive directions. Okay, this was very natural in dimension 1, but when you go to higher dimension, well, what should you look for? Real direction, complex dimension, real direction, complex directions, real directions inside complex directions. All those, right? So let's start with the trivial case, well, a trivial case where we handle this, because this trivial case, well, or particular case, give you a hint of what to look for. And then I have 15 minutes, right? Okay. So a special case. Well, a special case is the case where you have a homomorphic curve, which is invariant, passing through the origin. Okay? So you have there exists psi, which is not the same as before. Let's go with phi. From C, 0, 0, homomorphic, fixed in the origin, well, sorry, sending the origin to the dimensional one, such that after total psi prime of 0 is contained inside of 0. So it's going to be something to itself. Okay, but it's not fixed. And F restricted to this curve is not given. So I have a 6 point on this little curve. Well, in this special case, now you know what to do. Okay, so in this case, let's consider restricted to 0, and it's like one dimension. So you can do whatever you do over there. So you got an answer. But this is a trivial case, and in general, you don't have a homomorphic environment passing through the origin. This is a very special case. So in the general case, well, this doesn't happen. So assume this is not the case.
Excuse me, Jasmin, why assume the first derivative to be
But I want it regular.
different?
Oh yeah, sure. Sorry.
Otherwise, it's singular, then it probably
Yes,
can blow
yeah,
up.
I wanted to be sorry, it's just because it's in Friday morning and I have one this minute. Oh, this is going to be recorded. Fine. All right. So involved in a special case, well, you have to name again two people. But now, well, soon enough, we will have tendencies to work in this. I mean, it's a new window. In the general case, you don't have, so no invariant one first. Oh, there we go. At the origin. And let's fix some notation. So for some reason I can't here. Now we pass the variable x, and I want to take the notation. So x is in CP, and f of x is going to be x minus 1 over h, aka h of x, plus I of h. So this is homogeneous. Okay,
So the observer is cables too.
yes. I'm sorry. I'm really sorry. It's just I'm really violent. Yes. Thank you. I see you listening if you all know about this. Okay. So the fundamental results. I hope I'm not mistaken. I'm checking my historical records. So the fundamental results in this case go back to, well, they're not so old, but they're not so new either, and they go back to Jean Lecal. So I know the dates just to give you an idea. So this is 1985, and this is 1998. So, well, these results, they make use of, well, Eckhart's theory of more calculus and resurgence. So, well, these are well, techniques were not known by everybody and are somehow, I would say in a polite way, somehow obscure to most of us. And what Akim did, they were, well, they were actually in the same department. Akim, well, was talking to Raquel, and she decided to, well, give analytical proof of these results. So I would say at least the statements and the original proof that I can read are due to Raquel, and the proof that I can read and reproduce are due to Akim. And what they do is the following. So there's a key observation that you can find in Akim's work, which is the following. Okay, if xm, which is, well, the amplitude of x, converts to the origin tangentially to a direction v, a complex direction v, then, and well, I'm putting it like this because it's living in the projector space, then, well, h of v, this h over here, is going to be either 0 or you can choose, so we can choose a representative of v so that h of v is v. And moreover, xm is going to do exactly what it was doing in dimension 1. So you're converging to the origin, like my direction over n to the power 1 over k. Okay, so again, if you check Akim's paper, this is not the definition that you will find, but this is the definition that I will use because I find it easier and because this is what I used afterward. Okay, so in this case, I'm going to use names for these people. If we are in this case, we say that V is a degenerate characteristic direction. And if you are in this other case, so in the second case, well, V is a non-degenerate characteristic direction, and the special representative that I choose, V, is a non-degenerate characteristic vector. Okay. All right, so I have 10 minutes to finish. So let me tell you what a case result is. So it works. What a case growth is in any dimension. Whenever you have a characteristic, a non-degenerate characteristic direction, you have a parameter. Actually, you can be more precise than that, but this is what you have to have in mind. And the idea is that you will have as many as you agree, at least. Okay. And you will also have the value ones, nobody cares about. So I think I want to give a better, yes. Okay. Well, here. So the rough statement is B as non-degenerate. Well, you have a list. K, parabolic Q. And when you have a degenerate characteristic direction, so this is the one-dimensional pedals. And now you want to say something on the higher dimensional pedals, and to say something on the higher dimensional pedals, you have to say, to use a bit more the fact that you have this H over there. And so let me really sketch it. So to B, we can associate a matrix, well, an equivalent class of a matrix, and if such matrix has exactly B plus 1 eigenvalues with positive real parts, simply positive real parts, and this B plus 1 is counted with multiplicity, of course, then we have at least K D plus 1 dimensional. And we can also more precise, but I want to say something more recent about this. So on this section, plus we have two coordinates on this. All right. So in the 7 minutes that are left, so okay, let's make a statement. I will not say anything about the geometric approach. Okay, you will have to write me one more time. But let me tell you who are the people who worked on that, on this kind of results, after the results are clear. Of course, you can ask now what happens in the degenerate situation. Okay, and when you try to study the degenerate situation, well, RNA here, and also Spanish ones, American ones. So let me try not to forget all my friends. All right, and my PhD advisor, and one of the organizer. So, well, dealing with degenerate characteristic direction, So about it. That's one, two, lovers, a bunch of Spanish people. So lovers alone with sons. With myself, sons and Vivan. I think I forgot about the traveler. I forgot that one. I mean, there are a bunch of people. Okay, should I? So let me put 3 dots and excuse myself with all the people I have not mentioned today. Okay? Yeah, and there is a very recent one of which that I didn't get, and I didn't know where I got that. I include that and move on. Just got that. Yes.
No, I think I never worked with the general electricity direction. Thank you, anyhow.
No, mostly. Let me do the most. Yes, you're right. I think you're right. Mostly dealing with the general electricity direction, which is still correct.
Yeah.
So, and the idea, but this case, all these people, I didn't meet their people yet, so I don't know what they do. But in here, the idea, don't take it wrong, is to use similar techniques to Akim. So what Akim does is the following. So let me say in 2 words what Akim's technique is. So Akim's strategy is the following. So first, you change coordinate a finite number, but still very long number of time. So change coordinates. Now in a mysterious way at first side, so that you simplify your map with a good form. And now you get, so yes, so now you get a bias space of homomorphic graphs. And you define, so you reduce, to reduce to a bias space of homomorphic graph, where you define for shear lines. That and uses that to construct the contracting code. And whenever she has this, so these graphs, where here, these homomorphic graphs, whenever she has this contracting operator, then she will be able to find in the multi-generic case the parabola, like fixed points. And what it is hidden in all of this what it is hidden in all this is that, well, when you first read the proof, then you feel like these pedals are unique, which is hard to be the case. I mean, you change coordinates so many times, and you restricted the domain of definition of the graph so many times that, of course, at the end of the day, that makes sense. But, well, when actually you read here, whenever you are here, then whenever you have this coordinate, then you can, well, I would say, straighten your dynamics. And when you have your straight dynamics, then you see that you have plenty of parabolic shapes. Okay, and air techniques just give you the one that you can see in this kind of techniques. So let me just spend 1 moment and say what we are doing with wave and hands. So I will not write anything on the board, promise. So there is what we are doing with Xavier is trying to find a more geometric proof of what she does. And first of all, we're trying to understand, for example, what we were able to understand is where are these change of coordinates coming from. And you can see, for those who know, von Kerr-Dulac for normal forms of vector fields. And by using this kind of thing, we're trying to have a more geometric way of proving this result in order to get, hopefully, a new proof. Well, we already have a new proof of a Kim, and a new proof of some of these results, and maybe more. Because, and let me just finish on this on an open question. So in dimension 2, we now know, thanks to Rosas and Lopez here, that we always have, even in the degenerate case, a parabolic curve. I'm finished. So this is something that we know in dimension 2. So what happens in any dimension? You have characteristic direction, but you always have a parabolic curve attached, at least one attached to this characteristic direction when it is degenerate. We have some partial results by a bunch of people, but we don't see the picture yet. So let me stop here. I'm still giving you 1 minute of your time, so I thank you very much for your attention.
It's just a question.
There are none.
Anyone?
Oh.
Closer to the question.
Oh, yeah. Sorry, just being happy.
We're listening, but
Here.
Gautam, can you talk?
I think it's Michael's off.
Your microphone is mute. You have to unmute.
Oh, sorry. Yeah.
Hi, Doctor.
Hi, how are you? Can you hear me, first of all?
yes.
Oh, super. Great. Good to see you. Now, I'm afraid this is actually just a technical question. But I suspect it has got something to do with, the precise computation of your non-degenerate characteristic directions. And the really silly question is, if I have a holomorphic vector, if I have a homogeneous vector valued function of degree k plus 1, if I just scale it by a constant, it still remains a homogeneous vector valued map of degree k plus 1. So I was sort of curious about the normalization 1 over k, because you are probably presupposing something about some of the coefficients, right?
Yeah.
So what is the issue here?
So actually, it's just to make my life easier. So the minus 1 over k is coming from dimension 1. So I want to have as less coefficients as I can do. And so we are mimicking what happens in dimension 1. And in dimension 1, in the proof, as I was saying very, very fast, you put a minus 1 over k, because when you do like that, it's easier to write down the semi-conjugacy with the translation by 1. It's just a matter of, I want to make my life easy, and I want to use as much as possible of what I know from dimension 1 in my computation. And so there is no reason. Actually, if you read, for example, Marco's papers and the original Kim's one, there is no minus 1 over k over there.
Okay, right.
But actually, there is one thing that I wanted to put. So this minus is there because there is always a sort of a bit of confusion. So there are some people who say, or put a minus and say they're positive, the eigenvalues have to have positive real part. And on the other side, there are people saying, okay, I don't put a minus in front of my map, and then I want these eigenvalues to have negative real part. And so, well, okay, let me be completely honest. I wanted to be on the second side, but Xavier fought to be on this Achim side. And so, well, you know, I didn't want to fight with Xavier. He's big enough. So, well, that's how it worked.
I see, right. All right. Thank you so much.
Thank you very much, Doctor.
Any other question online? Yes, not. So what about in yes.
Well, in my understanding of team and this stuff, what I always thought, although I never formally prove what I'm saying, is that you can consider your tangent to the entity map as the time one flow of a vector field, which unfortunately is formal many times. And in fact, I think Lopez and Cano and Bruchero, they use this approach to give another proof of Achim's theory, because what you do, so the change of variable, they are actually blowing up and then desingularization of this divisor. So in dimension 2, you have, I mean, things works pretty well, but in a higher dimension, there is this problem that you might have singularity which are not isolated, so you might blow up along a subvariety or stuff like that, and it's not clear to me how you get this existence of parabolic curves. So I just wanted to understand what is the new geometric point of view that you have with Xavier, just in few words.
Here, so actually in few words, the idea is that we get rid of this part. We get rid, so we change the Banach space. We have another lemma which is, I think, quite classical. So on contraction of graphs, okay? And the idea is, so here you have, as you said, thanks for saying, you do a blow up and then you change coordinates. And I'm changing the blow up. So instead of doing a standard blow up like you would do in algebraic geometry, I do a change of coordinates with an epsilon, which is similar to a blow up. It's like what we call the 1 plus epsilon blow up. And it gives you the space you need to avoid resonances. So you're completely right. You have this vector field going somewhere, and the resonances that you're considering are the real ones. This is why you have a real part example. Okay, so you're considering real resonances, and what happens is that if I put an epsilon, I have enough space to kill the problem that I have with these resonances, and I'm just able to apply this more geometric lemma, which is, and in there are some populations.
Is it equivalent by saying that you have your formal vector field, you approximate with the holomorphic one, and then the flow approximate and then use this really holomorphic vector field, or is it a different story?
Say it again.
I mean, you have the formal vector field for which your map is the time one flow, let's say. Then you can approximate the formal vector field by polynomial effect vector fields. Then you can consider the flow.
Yes.
What it was, well, I never worked out this, but anyhow, and it's not clear to me whether you have some kind of uniform convergence in some parts, and so this epsilon that you use is a different story.
No.
Okay.
You don't have, I mean, if I understand it correctly, you don't have this sort of convergence, which is why it is so damn difficult to work with that.
Yes, and I added to this in dimension 3 or more that this formal approach misses parabolic curves even in the non-degenerate case.
Yeah, you're right.
Yeah, exactly.
So that's
They did only those which survive to blow up the state,
Exactly.
which goes wrapped in the exceptional divisor. They don't, yes.
Thanks.
Another question or not?
Yeah, just a quick question again. By resonant, did you mean resonant in the sense of the Poincaré-Dulac theory, which is that you have a linear relationship between the eigenvalues?
Yes, and actually it is so very good, yeah, by the way. You remember this stuff. Thank you. So yes, it is exactly that. So this is what happens in here in the change of coordinates. You have some relations in between the eigenvalues, which are of additive form. So you have additive relations. Oh, well, okay. Let me really be technical for 1 second. We'll put yourself in the situation of having to put logarithm in here to get to a good form. Okay, so your changes of coordinates will contain logarithm because it's like log of x, and they resemble, if you think about it, if you know about it, to transseries when you do it formally, because you have this kind of additive resonances, which is kind of weird to find out here, because usually when you're talking about equation of homomorphic maps, you have multiplicative resonances in between the eigenvalues. But it is not so weird because it is additive resonances in between eigenvalues, not from the linear part. They're coming from the first nonlinear term. And so, well, and actually, as Filippo was saying, they're coming from the fact that you have a hidden vector field, which is not a vector field because it's a formal vector field. So, well, entering into the picture. And I didn't put all these details in here because I didn't want to kill you.
Thank you.
Thank you.
Okay, so thank you again. At 5:11. You want to copy, you know.